So, to understand the behavior, now here we are going to take 4 different cross sections to study what is the effect of equivalent steels, okay, not equivalent. So, for example, this pure prestressed and passive reinforcement is an equivalent section. So, now why do I say equivalent section? Just like we have done in the axial behavior, I am going to say AP times Fy for normal steel should be equal to AST times, sorry, this should be AP times FPY should be equal to AST times Fy, okay. So, this the tension force at yielding is going to be same for the equivalent section. So, now how do we do that? We have seen that FSY or the yield stress for passive reinforcement is 405 megapascal, FPY for pre-stressing steel is 1618 megapascal, right. So, you can see that, right, 1618 megapascal, right. So, in this way you get roughly, if you see here, if I multiply 4 times FSY is equal to FPY. So, 4 into 415 is roughly about 1660. So, that is nearly same. So, that is the reason we are taking 4 times. It is not exactly same, but nearly same. So, just to get an idea, right. So, that is the reason that we are getting like this, right. Okay. So, this is the steel. So, that is the reason I have taken here 600 for pre-stressing steel, 600 times 1618 is one tension steel, that will be nearly equivalent to that of 2400 multiplied by 415, nearly equal, I should say nearly equal, because I cannot take a I wanted to take a round number so that you can comparison becomes easy. So, in that way they will be nearly same. So, they will be nearly same, okay, right. Now, let us look at, so for this is a problem for different things. So, this is going to compare, if I have equivalent steel, what is the behavior in moment curvature between a non-prestressed reinforcement section and prestressed, pure prestressed section. This example will tell you what will happen if I put a compression steel. So, this is only compression steel, right. Now, this is similar to your a doubly reinforced section. I have compression steel ASC and I have AP, then I have AST as well. So, all the 3 combinations are put. So, let us see what is the effect of each of these individual reinforcements. So, again I have stretched this to 0.0065, right. This is our initial stress. So, initial stress how much? 0.0065, right. So, you can calculate it is roughly about 1200 megapascal is what initially we stretch them up to. So, 0.75 times FPK, that we have already done it, right. So, 0.75 times FPK is what we are going to put. So, that will roughly comes to around 1240 megapascal. So, you will get that. So, this Fy for the non-prestressed steel is 415 megapascal, modulus of rupture FCR, right. I am taking it to be 10% of the compressive strength, which is quite a good approximation, right, 4 megapascal. Now, with this assumed properties, let us see how the moment curvature response for a different cross section is going to look like. Now, the first case is pure prestressed. Again, we are stretching it to 0.00. Let me see. 0.0065 multiplied by elastic modulus of 195 will give you about 1245 megapascal or so, right. So, let us look at it now. Yeah. Okay. So, this is what we have, a cross section. Now, what we are going to do is, this is the amount of pre-stressing steel that I have. Again, this has been stretched to a strain epsilon pi of 0.0065, right. Now, FPI is going to be again epsilon pi multiplied EP, and note that EP is 0.0065 multiplied by Now here 195,000. So it will roughly will get out 1245 megapascal or so. Okay, we will calculate that. Okay, so you know all these things. So what is the procedure? We are going to assume epsilon c and keep increasing that epsilon c and iterate x and find that what x it will satisfy this force equilibrium c is equal to t. So I can express everything in terms of x, right, and then solve for it. Once the strain distribution is known, then I can calculate my strain Fp, which is basically function of your epsilon p. And similarly, this stress block again, we are going to convert this into equivalent stress block like this, right. This is alpha 1 F prime c, this is beta 1 at the x, this is your Cc, right. So this is what it is, right. So let's see how do we do that. And we will explain the step-by-step procedure. Finally, I want to get this kind of curve. So these are the salient features if I complete this exercise and I get different values of moment and curvature like this, starting from here, different points that I get. And then finally, I stop here at certain point corresponding to this is your ultimate condition. Right. So now how do we get all these values? So for example, when that strain is negative, so that means it is in tension, you get the curvature of this, right, and 0.0035, I get curvature of 28.065 and a moment resistance of 593.5. So we want to establish all these different moment and curvature corresponding to different values of your epsilon c. Now let us see for one chosen value of epsilon c, how do we calculate this moment and curvature. So we have taken this, for example, let us say this corresponds to when there is no external, there is a negative curvature, this is caused by initial prestressing force. This is what I said, this is your initial curvature, negative curvature, which is minus 0.9 into 10 to the power of minus 6, 1 by millimeter. Right, curvature is the rotation per unit length. Okay, that is the reason the unit is 1 by millimeter here. It's so small value and it is in the order of 10 to the power of minus 6. Right, because we are talking about one section, how much it is rotating. When I measure that, multiply that with plastic hinge length, that will give me the total rotation of a region, right. So anyway, so let's look at now how do we calculate. First, the calculation of the initial curvature. Now, how do we get that initial curvature when external moment is 0? How to get that initial curvature value? And we know what is the initial pre-stressing force that we are putting, that is 0.0065, because this is your epsilon pi. Epsilon pi multiplied by EP, I told you it will give you the initial stress Fpi, that multiplied by area of pre-stressing steel will give me the force. So we are applying a 760.5 kilonewton initial force, and we know the sectional properties. The area is 650 multiplied by 300, this is this, and moment of inertia is this, so BD cube by 12, and then section modulus is BD square by 6, so you get this value, and elastic modulus we know it is 5000 square root of FCK, and F prime C is 40, FCK will be 41.75, we have already established that, so you substitute that value, you get 32,300 megapascal. And now that we know this, what is the moment that we have applied? Now curvature is nothing but, again we have established, it is nothing but m by EI. Now what is the initial, when there is no external moment, there is only pre-stressing moment it is there. That pre-stressing moment is P into eccentricity, right. Now P we have calculated, what is the eccentricity of that force? If you go back to the cross section, you see here, this is the cross section that we have 650 and this is at 300, 600, right. So the eccentricity is going to be, so this is going to be from here it is basically, so total is, this is going to be 325, right. So 325 and this distance is at 600, so basically it is going to be 600 minus 325 is your eccentricity. This E is going to be 275, right. So, that is what the eccentricity of the pre-stressing force is. So, if you go back and apply this, eccentricity is 275 and E is already we calculated, I we have already calculated, you get an initial curvature of 0.942 into 10 to the power of minus 6 per millimeter. Okay. Now, how to calculate the again the initial curvature? Again, we can calculate the stress at the top fiber because at this point of time only pre-stressing load is acting, right. So, we have studied in the previous modules how to use the stress method of analysis. So, stress at the top fiber will be minus P by A and pre-stressing moment will create, there are two components, concentric component and the pre-stressing moment. Pre-stressing moment is going to produce tension, that is why we have plus here. You substitute the values, you get a net stress of 6.012 megapascal. So, you can see here what is the amount of pre-stress for this, what is that we can infer. When there is no external load, this is actually greater than 4 megapascal, which is actually not good. You have actually applied too much pre-stressing and this has gone into when there is no external load. Note that when the no external loads are acting, this has exceeded 4 megapascal by 2 megapascal. So, you will have a lot of cracking at the top. So, we have to keep that in mind. Now, what is the strain in the top fiber? 6 divided by this elastic modulus, roughly, we are doing a rough calculation. So, you are going to get 0.000186 and assuming that this is again assuming because it is slightly exceeded. So, I am assuming linear, which is not exactly correct, but we are just doing a quick calculation. So, let us say that this. Now, at neutral axis the resultant stress has to be 0. So, if you substitute that stress equation for at a distance y is equal to the stress has to be 0, then you see here it is going to be minus P by A plus P E into y by I is equal to 0 and you can see that P by A is 3.9. So, this and both of them should be same. So, y works out to be 128.1 millimeter. So, the neutral axis depth is 325 minus 128.1, which is 196.9 millimeter. Now, why is that we need that is so that phi I can calculate from epsilon c by x. So, x, this is your x and epsilon c is this. So, now that I got both the values, what I can do? I can calculate the curvature. Okay. Okay, so, this is the way that we are calculating. So, if you substitute these values also, you will get the curvature to be same values. Now, so another important, so this point we have calculated, there is no external moment. There is also one more important point. I want to calculate how much should be the moment I need to be applied so that this curvature, the negative curvature becomes 0. If you see at this point, the curvature is 0, right. So, I want to calculate at what moment it is becoming 0. So, you know that I need to exactly apply equal moment of external moment equal to the hogging moment due to pre-stress. Now, what is the hogging moment that we apply due to pre-stress? It is P into E. It is pushing the beam to rotate on the opposite direction, right. So, if this is going to be m is equal to P into E and this is the moment that we applied. So, basically it should be kilonewton meter, right, and we are trying to calculate. So, this should be the moment. So, this value will be roughly 209.1 kilonewton meter. Okay. Now, we got the initial curvature when moment is 0, we got moment that is required to make the curvature to 0. Now, we are going to calculate what is the cracking moment. So, the cracking moment will happen when the moment at the bottom fiber reaches the modulus of rupture. So, again FCT or FCR, whatever that you want to calculate, that is 4 megapascal is given to you. An axial component is 3.9 megapascal. Pre-stressing moment that what we are getting is negative 9.918 because now we are calculating at the bottom fiber, right. So, let us say that this is what the section is, right, and I have prestressing like this, okay, AP. Now, what we are trying to calculate is, there are 3 components, right. So, one is this negative P over A, because we are calculating the stress at the bottom, okay, we are calculating stress at the bottom. So, we are calculating at this, we are calculating at this fiber, the bottommost fiber. So, this is negative P by A, and then we have prestressing component that is actually going to create negative and positive like this, which is P into E divided by Z, P by let us say section modulus, right, and this is going to be negative, this is going to be positive, right. And next, what is this? And I am going to have external moment that is going to create tension here and compression. Okay, that is going to be plus and this is going to be negative. So, at this location it is going to be M cracking by Z. So, that is what we are saying, this is your Z, and this net everything should become a tension stress of 4 megapascal like this. This is plus, this value is 4, right. So, this plus this should equal to this 4 megapascal. So, stress at the bottom we are doing P by A, which is 3.9 negative, and this is negative 9.912, and this is what we are calculating, so that the net becomes 4 megapascal. So, this is what we are doing. So, if you substitute that, you get your M cracking as 375.83 kilonewton meter. Now, what are the stress at the top fiber? Again, it is compression, this will become tension, this will become compression. So, it becomes 11.18 megapascal. Now, strain, because when the stress is less than 40% of your F prime C, we can assume that it is going to be linear, typical, okay. So, that is the reason stress divided by elastic modulus will give me the strain quickly. Now, again, why is it we are interested in calculating the strain? I want to calculate the curvature corresponding to cracking, right. We got this strain, right. Now, how to calculate the neutral axis depth and curvature at cracking moment, right. At neutral axis, again we know that the stress is going to be 0, and axial component, again prestressing moment component, and this is the moment MCR that we are applying, and we are calculating at a distance of neutral axis where the stress is going to be 0. So, if you equate everything to 0, you will find expressions for your y or x, whatever that you want to call it, okay. So, this you say that it's multiplication symbol, right. So, if you substitute x works out to be 485.7 millimeter. Now, because the predominantly the entire cross section, this indicates what? Most of the section is in compression, right. So, epsilon c by x will give me 7.51 into 10 to the power of minus 7 per millimeter, right. So, this is the curvature at the incipient of cracking. So, when the stress reaches FCR, this is the curvature. After that, the stiffness will be lost and the curvature will increase dramatically. Okay, so what we have done, we calculated this point and we calculated this point, now we calculated this point, right. So, this is the cracking point. Now, let us look at this is what we have done. So, next point is let me increase the moment to a slightly a higher value, which is 0.0005, very small strain. I am just rotating the section slightly with a top compressive fiber strain of 0.0005. It is very small strain. So, once epsilon c is fixed, now we are looking at this point, right. So, we are trying to calculate. So, this I am saying that epsilon c is 0.0005, okay. Once epsilon c is fixed, I can get my beta, which is 4 minus epsilon c by epsilon prime c divided by 6 minus 2 into epsilon c by epsilon prime c, I get a value of 0.682, and alpha I know it is 0.336 again from the equation that we derived previously. And compression, once alpha and beta is known, and let us say that I do not know what is x, neutral axis depth, right. So, I am expressing this as an independent variable. So, I have pressed all the values that I put it, then I take this as 2750 x. Now, because my strain is very small, I am assuming that the pre-stressing steel is not going to yield, because this is very small. I am assuming again pre-stressing steel not going to yield. Okay. So, that means pre-stressing steel, if we go back, and this is what we have taken, Fp epsilon p, and you see this is what we took, right, and this was some this was epsilon py, we had taken it to be 0.0083, Fpy was 1618 megapascal, and this was ultimate, right, which is 1860 megapascal, and this was a higher value. And so, now that, so basically what we are saying is we are somewhere here, okay, somewhere here before yield. So, for this strain we are saying that pre-stressing steel we are in this regime. So, I can calculate Fp as Ep into epsilon p, where this slope is Ep. But if this epsilon p is going to be very high, then I have to use this slope, which we have already calculated to be very low value compared to that of this is 195,000 megapascal, but this is very small. I think we have given that value, right. So, we have to see that. So, here in this case I am going to say now from strain, this is from strain gradient, right, from similar triangle I get this delta epsilon p, that is happening because of that epsilon c that I am assuming, right. So, again this can be expressed in terms of x. Now, what is epsilon p? This is the initial strain epsilon pi, and this is your delta epsilon p. So, we sum them up and get your epsilon. Now, this net epsilon p, I am going to say that this is going to be less than epsilon p. I am assuming, I have to check again whether that assumption is correct or not, right. So, let us do that. So, once we do that, this is the epsilon p multiplied by Ep multiplied by Ap will be give me my tension force in the steel, right. And this the entire thing, if you look at it, right, what is the equilibrium condition now? So, this can be solved, right. So, if you substitute that Ts equal to Cc, again Cc again we formed one equation in terms of x. So, I equate both of them, and the entire thing can be expressed in terms of a quadratic equation, and I can directly solve for x as 298.1. So, once x is known, now I can go back and calculate Cc. Again Cc is alpha f prime c beta x into b, right. So, only x was not known. Now that I found x, Cc can be calculated. Similarly, now how do we get your moment? So, the moment again, if you go back to the cross section where your steel is, and this is the strain gradient that we have assumed, right, and this is your delta epsilon p, and this is your epsilon c, which is 0.0005, very small value, and this is your epsilon pi, right. For that we get some stresses, and we converted this into an equivalent rectangular stress block, alpha f prime c beta x, and this is your Cc, and this is your T, let us say Tp or Ts, whatever you want to call it. Now, when I take moment about this, and this is going to be at a distance, we know at a distance of beta 1 x by 2. So, this lever arm is going to be d minus beta 1 into x by 2. So, if I take moment about this location, it is going to be Cc into lever arm, which is, let us say, Z, we call it distance. This is nothing but your Z. Cc into lever arm Z will give me my moment resistance. Now, again we have to go back and check whether Cc is equal to, because that is a condition that we have enforced, Ts is equal to Cc. So, directly you get it, right. But from the strain we have to still assume that epsilon p is still less than epsilon p, because we have assumed like this. If this assumption is not valid, then we have to change it, right. Okay. Now, the curvature is epsilon c by x and I get a very small value. So, you see, for one value of epsilon c we have assumed, we have calculated now one moment value and one curvature value. So, that is what we have done, and like this you can continue for different values of epsilon c, right. So, now what we have taken 0.0005, then I take 0.001, I take 0.002, then I take 0.0035, and I get different values of moment and curvature. So, in this way I can generate the entire moment curvature curve. Okay, that has been already done. That is what it was given here in this table, if you see, right. Yeah. So, this is the value. So, we got this value, like this I can get family of points until the section collapses, right. So, that is what we have done. Okay. So, this is what we have. So, this way we got the entire regime, this entire curve is what, how we get your entire point, right. Okay. Now, let us see the pure prestressed section. Right. So, we went through all these things. Okay. Now, let us move on. How do we do the analysis for the next case, which is a passive reinforcement? You see again 2400, and that is an equivalent steel. Roughly it will be 4 times, because 60 is roughly your yield strength for the steel that we have taken, and 4 times of the steel equivalency. So, we had pre-stressing 600, here I have taken 4 times, because yield strength is roughly about 4 times, right. So, that is the reason I have taken like this, so that we can compare apples to apples, right. Now, the same exercise we do, epsilon c we assume, and we iterate for different x, and using strain gradient I can get my epsilon s, then I can get my stress distribution. I need to make sure that c is equal to t and choose the value of x that satisfy the equilibrium condition, and so on, same like what we have done. Only thing is, here there is no pre-stressing, so epsilon pi is 0 and epsilon s is nothing but equal to epsilon c. Compatibility is only this, right. The strain is there. I mean, when I say the strain at the level of steel, right. Okay. So, the only unknown here is x, right. So, we can redo those exercises, and we can calculate different values of moment and curvatures for different strain that what we assume. So, one thing to note here is, let us see, this is what we get, this is what finally we are trying to achieve. Now, let us see how do we get that for. So, if you go back, this is your cracking moment, okay, this is your MCR, okay, and now you see the section dimensions are all same, 300 by 650 for both pre-stressed as well as non-pre-stressed, and they are also having equivalent steel. That means the tension force at yielding from non-pre-stressed section and pre-stressed section is nearly same, right. So, let us look at now the first point, how do we get it, right. So, let us cracking moment. So, the cracking moment is a moment when the bottom fiber stress again reaches the modulus of rupture, and MCR by Z, and Z we have already calculated, section modulus is 2.11 into 10 to the power of 7, that should equal to over 4. So, I just directly get MCR very simple way, 84.4 kilonewton meter. Now, stress in the top fiber again 4 megapascal at this condition, strain is 4 divided by elastic modulus this. Now, again, so why is that we are doing this again? Curvature is epsilon c by x. So, I can quickly get my curvature, right, strain divided by the neutral axis depth. Strain I have got it, x is in this case is going to be exactly at the center, which is 325. So, I can get curvature as 0.00012 divided by 325. So, which will give me the curvature, right. So, you get this value as 0.369 into 10 to the power, very small curvature. So, reinforced concrete is going to crack at a very small curvature, positive curvature. Here it is positive. Okay, that means the section is bending like sagging bending that you have. Okay, so you get this point. Now, I want to find out the next point. Okay, so this we have calculated 83, and this is a very small curvature that we got 0.369. Now, I want to do this next point, that would be at some strain epsilon c. Let us assume some value, and like this, I am going to take a very small value of 0.00025. Okay, epsilon c. Like this, we are going to keep iterating for different values. Now, this is my ultimate condition. Okay, usually ultimate condition is when epsilon c at top reaches 0.0035 or steel at bottom is going to rupture. Okay, either one of them, right. But most of the cases we want to make sure that the steel is not going to rupture, just it is going to yield, and before that concrete will fail. Okay. If the steel at bottom is rupturing, that means you have provided very less steel, which is also not good. Okay. So, the curvature we can calculate epsilon c is like this. The moment this is what we are trying to see, find to find moment in curvature corresponding to a small strain of this value, right. So, once epsilon c is fixed, I can get my beta 1 and I can get my alpha 1, and epsilon prime c, it is equal to 0.002. So, you put this value, directly get your beta 1, alpha 1, right. So, that is what we are going to do. We get your beta as 0.674, alpha is a very small value, because epsilon c is very small, right, and compression forces alpha 1 f prime c beta 1 into x into b. So, again express this in terms of x. Because my strain is small, here I am again assuming that the steel epsilon s strain is going to be less than yield. Okay. This is the condition that I am assuming, that again I have to verify that, right. If this is the condition, I can directly solve in the form of a quadratic equation, right. So, this is from strain compatibility, again epsilon s is 0.00025 divided by 600 minus blah blah blah. So, I am taking epsilon c, right. So, using similar triangle, you get this epsilon s, and this can be again expressed in terms of neutral axis depth. Now, the tension force is nothing but strain multiplied by elastic modulus multiplied by area of steel. This is AS, this is ES, and this is your epsilon s. And here I am assuming that epsilon s is less than epsilon y, right. Then only I can express like this, right. Then this is the condition. So, when you equate Cc equal to Ts, everything can be formed in the form of a quadratic equation like this, and then I can solve for x, which is 185.92 millimeter, right. Then you substitute back, you get your compression force as 267 kilonewton. My moment, again I take moment and leave around with this, Z is nothing but you see d minus a by 2, where a is nothing but beta 1 into x by 2, right. So, we substitute that, you get your moment resistance as 143.6. Now, curvature is nothing but epsilon c again by x. So, you substitute the value, you get your curvature. So, for epsilon c of 0.00025, you get one moment and one curvature, and you got the value. So, like this I can continue for different epsilon c and I can generate the entire curve. Okay. Now, we are doing it for only one calculations to show how to do it, but you can do it for the other strains as well and then generate the entire moment curvature response, right. Now, let us look at it. The third case is pre-stressed section with compression steel. So, here AP I have taken it to be again 600 mm square and I have some compression steel. Let us see what is the value, but these are the sections that we have already given there. Right. Again, the moment you have pre-stress, now I will have epsilon pi and delta epsilon p will be there, and delta epsilon p is coming from the externally applied load that creates the strain profile, but epsilon p is the initial strain and this is the stress block and we convert them into an equivalent stress block. Now, only thing is in this location now, based on the strain that you have here also epsilon s c, the steel is also going to be in compression. So, the steel is also going to give me some resistance in compression. So, Cs is nothing but, right, the stress in the steel in compression multiplied by the area of steel in compression, right. So, this is the X bar. Now, you have two things, concrete also provides compression force, steel is also going to give some internal compression force. Now, together I can find the centroidal location of these two forces. We know concrete is going to be at a distance of, what is this location? For concrete is going to be at a distance of beta x by 2 and steel is going to be at the location wherever you are providing the steel. So, that distance let us say that as k. So, you can find the combined centroid of this Cc and Cs in this way. So, this is the taking the moment of this forces about the top location. So, that is what we are calculating X bar. So, X bar can be calculated because it is easy for me to calculate my moment resistance in terms of one equivalent compression force which is Cc plus Cs. So, C here is nothing but Cc plus Cs from concrete plus from steel in compression multiplied by the lever arm. In this case the lever arm Z, this is the lever arm. Now, what is the lever arm here? D minus X bar. Now, this X bar is I calculate from this combined location of your compression force. Okay, so, like that we generate for different values of strain and we get this entire regime of this moment curvature behavior. Okay. Again, because of you have pre-stress, I will have initial curvature like what we had and I will have moment that has to be applied to make the section coming from camber to 0 level, curvature to be 0, and then you have cracking, M cracking, and then you have yielding and so on, right. So, I generate all these points and then I get my entire moment curvature response. Okay. This is for a section with prestressing steel at the bottom and compression steel at the top. Okay. The process is same, you increase your epsilon c and you iterate your x to satisfy your equilibrium condition, then you find one value of m and one value of curvature. So, you repeat the process, right. Okay. So, now you see here one thing that to note down here is I did not go all the way to epsilon cu of 0.0035, 0.0035 I did not go, I stopped at 0.00240. So, why do you think so? Because the ultimate condition can happen when the concrete either reaches first 0.0035 or steel at the bottom can reach a rupture strain that we have calculated epsilon pu, if you remember, to be 0.022. Right. So, in this case the steel at the bottom was actually rupturing. So, the concrete cannot go all the way to 0.0035, but it can go only up to 0.00240, right. So, that is the thing. So, in fact, the provided steel is so less, it is happening like that. So, we need to provide, that is also one condition, this is not a good failure, it is not a good failure. We want concrete to fail in compression after steel yielding, right. So, this is not a good failure. So, but you have to keep in mind, that is the reason we have done till here. So, this ultimate state will be explained. Here the reinforcement is low and it will be reaching its ultimate before concrete reaches its 0.0035. So, this point you have to note down. Okay. Now, let us say I am assuming epsilon c of 0.0025. I am explaining how at this ultimate point how do we get your moment and curvature. Okay. And here, because we already done that exercise, we know at this strain pre-stressing steel is reaching its rupturing strain before concrete reaches 0.0035. This is my ultimate condition. Okay. For this strain, now let us calculate how to get the forces. Once epsilon c is fixed, beta can be calculated, alpha can be calculated. Compression forces alpha 1 f prime c, beta 1 x into b. This can be expressed in terms of H640x, and delta epsilon p from the strain gradient, again I can get this in terms of xu, right. And here again, you know, you can get your epsilon p like this. This is your delta epsilon p, and this is your initial strain. Now you see here, this will not be in the initial slope, but because, you know, right, this is your Fp and this is your epsilon p, right. Now I put less steel, right. So this is, we have taken to be 0.0083, and this is your 0.022, and this is 1618, and this is 1860 megapascal, right. So you see here, we are going to be in this regime for this case, right. So we are going to be somewhere here or here for this calculation, right, or maybe, you know, actually it is going to reach its ultimate, right. So I have to use this slope, not this slope, okay. This is EP, which is 195,000 gigapascal, and this is some slope that we get, some fraction of this EP. That is what we have to take. So now this. And epsilon SC, similarly you have a compression steel also, again from strain gradient I can take this similar, again this is from similar triangle, right. Now what is TP? TP is, now you see here, it is, this force is already reached. Now I want to do this incremental thing only. So I am here, somewhere here or here or here, right. So somewhere here. So that is the reason this is your yield plus some additional strain multiplied by, this is the slope. This slope is 17,394, right. So that is the reason this is only a fraction of what we take, roughly about maybe 17,000, right. So roughly about little less than 10%, right. So this is the stress strain curve you have to use, because you have to use a bilinear curve, and this is the way that you have to express. And CS, here again we are tactfully, we are assuming that it is going to be EP, and this is your area. Again this is ES, this is our ASC, and this is your strain, which is epsilon SC. So here we are assuming that the compression steel, because it is less than 0.0024, it is not going to reach its yielding, right. This is in the compression steel is still in the linear elastic regime. That is why to get stress I can directly multiply the strain with elastic modulus, right. This way I can get my CS, then I can equate that C is equal to T. So basically that tells me again one quadratic equation, and X, when I solve for it, I get my neutral axis depth of 79.58 millimeter, and compression force is, you know, you can calculate all 8640 times X, which is 79.58, gives me 688 kilonewton. CS is 428 kilonewton, and I get my epsilon P as 0.022. That means it's reaching its ultimate strain, right. And the steel is going to collapse before concrete reaches 0.0035. So that means the amount of steel what we have provided is less in this case, okay. This is not a good design. I need to have minimum steel so that the steel should not rupture. Steel should yield, but it should not reach its rupture strain, right. So then again I can get my moment resistances, combined compression force multiplied by this lever arm, I get 626.8 kilonewton meter. And curvature is again epsilon C by X, right. So like this we can calculate for different sections. So this is for ultimate condition, okay. So again for previous initial strains of different epsilon C also you can generate moment at curvature, and you can generate the entire moment versus curvature response, right. Now, let us look at the fourth case, okay, pre-stressed with both reinforcement. That means, I have both compression steel as well as tension steel in addition to AP of 600 mm square. Now, tension steel is 1200, compression steel is 1200, right. Again we go through the same process, everything else remains same. Now, in addition tension force, I have two components, both pre-stressing steel as well as this AST and FS is come. So, now both compression steel, compression C has CC plus CS, similarly T has TP plus TS. This is from pre-stressing steel, this is from normal non-pre-stressed steel. So, again the centroid of compression force still remains the same. I can take the moment resistance as C into D minus X bar like this and so on. So, now when you do the exercise, again you get your entire response like this. Let us look at now how do we do for one point. Again you will have initial curvature, you have moment at 0 curvature, and you have cracking, and you have somewhere here yielding. All those things are still there, right. This is your ultimate condition. Okay. Finally, we will compare how these 4 different sections responses of moment curvature compare with each other. Now, this is the value for this particular section, which has both pre-stressing steel and steel on the compression side and steel on the tension side, right. Now, we are showing calculations for one value of epsilon c, which is 0.001. Let us see how do we get this moment of 700 and curvature of 4.354. Okay. And we are going to show calculation for one value. Again you can repeat the exercise using a simple Excel sheet, and you can directly get this entire moment curvature response. Now, we are going to assume epsilon c equal to 0.001. Once epsilon c is fixed, I can get my beta and alpha values, and I can get my compression force in the form of x, neutral axis, as 5000 x, and epsilon p is the strain in the pre-stressing steel. That again from strain gradient I can get a very small value as like this, and okay, so this should be this, okay, this is delta epsilon p, I should say, this is delta epsilon p, and this is your epsilon pi, and this is your delta epsilon p, right. So, when you add them up, you get your entire pre-stressing strain epsilon p, okay. And similarly, strain in the tension steel can be calculated using your strain distribution that we have assumed, right. Again all of this is from simple similar triangle, okay, right. Now, the tension force Tp is epsilon p times this 195,000 multiplied by area, which is AP, again this is EP, and here I am taking it to be epsilon p. So, here we are assuming that the steel is because the strain is very low, I am assuming that the pre-stressing steel still has not reached its yielding strain. So, that means this epsilon p, I am assuming that it is less than epsilon py. Again that assumption has to be verified, okay. Ts now is basically again epsilon s Es multiplied by area of steel. And compression steel strain is again from similar triangle, this is from similar triangle, right, and compression force is again strain epsilon SC ES multiplied by ASC. Now, compression force should be equal to tension. So, we can again form, when you put all of them, you can form a quadratic equation and you can solve for x, and you get your value as 229.7 millimeter with a concrete contribution of 1148 kilonewton and steel contribution of 188 kilonewton in compression, and curvature of 4.354 into 10⁻⁻⁶.